Good evening, gentle readers. Welcome to another installment of Moment and Motion, a discourse on these two complementary concepts, yet complementary duals. The moment is things change their state, and their motion is things convey their state. Moment in motion. Study has been about classical mechanics and classical motion in a modern theory with regards to the paleoclassical, superclassical. The idea is that a deconstructive account of the dimensional analysis of classical mechanics and motion must incorporate the concept of the infinitely many higher orders of the degrees of acceleration, which as a plain mathematical artifice has no other recourse than to be what it is, and to have here from the big end and the little end respectively the meeting in the middle of basically from infinity and on down, all these ways to arrive at that there is rolled up enough of a notion that there's combined what results the classical law in the middle, force equals mass times acceleration, or the linear. And here with respect to these major notions of the moments, the inertia, and that is the energy that potentially a moving object has with respect to others in its environment in terms of its relative velocity of things, and its momentum, which is as of sort of the derivative of that with respect to time in a sense, or also as about the first term in the power series, where it's so that the first term in the usual Taylor series, the power series, is kind of this derivative, and then as with regards and with respect to why that's a quantity, and what came from after the time when it was made these notions of algebraic forms, and or as after the Islamic Enlightenment to the Mertonian school in Oxford and the calculators, when the great seat of this development came from Bradwardine and these and de continuo and the notions of power and resistance to complement the earlier discourses as by Aristotle and them, and what is our canon? What are the names of these considerations? And fast forward 100 or 2 years to Galileo, and to keep in mind the rich coterie of other people around. I mean, when they talk about somebody who's like, the sign of the times, the poster boy, Galileo Galilei, there are many others around him who help contribute the inputs to these things. Another 100 years to Newton and all his giant squad upon which he stood, and then as after that and into the modern day and the era, basically, given that the principles and the theory was so realized by Newton's laws, as it were, which are Galileo's and Copernicus's and Kepler's, kind of together. That then what I'd hoped here is then in the consideration of these various forms mathematically, is I've arrived at, what I'm trying to figure out is Zeno's swath. So a swath is as of cutting the edge of the field. So it's involved with these symmetries, submersions, and sheaves, the notions of the field, and the notions of the gathering and things, and the measure problem, how to analytically characterize how these things move around. And then one thing I'd hope to find would be some references in the literature to things of this study, trying to take this notions of distance and length as being two different things, yet they're in the same units, yet they're framed in terms of the time, like the action that happened over the course of a time that arrived at this distance's length. And so for one dimension, 3 and then 2. So trying to keep things simple, just turn the linear for the linear classical mechanics. Then as with regards to the rotational and kinematics in the classical mechanics, having that involved, how that maintains the inertia as the quantity, and that for the amount of energy in the system, because energy, if it's not necessarily always of the same form, is kind of considered conserved. Thusly, that's a hallmark of this system with these symmetry laws, invariance laws, and conservation laws. So accordingly, or here is symmetry, flex, quasi-invariance, and continuity laws. But then what we'll hope to arrive at is some more about that. So yesterday, or the last time, I was wondering to myself, well, how can I find some more about current mathematical developments that already have this in mind? So I wonder about who gets into this infinitely many higher orders of acceleration. There was considered this extraordinary differential analysis, a fractional derivative compared to the integer derivative, and that's a great thing. It's a continuous analog of otherwise a whole valued thing, so it expresses how something can be interpolated from value to value, and it's the study and understanding of the implicits that carry that as what's a straight line through a tautochrone or isochrone, a curved thing that goes around through this is the goal. And then there's the idea that somewhere in the mathematics there'd be more about taking these 2 dimensions up into 3 dimensions and figuring out from that this 1 dimension about time and length and distance, or distance and then time and then time, or otherwise about taking up to these 3 dimensions to get back to 1. Where usual course of dimensional analysis is rank lowering, because then you can solve something. Here the idea is to figure out how to kind of like project it up to a space and then find a natural line in that results this and that. Well, so I suppose I could use a shave and perhaps a haircut. But for the time being, I'll just set the clock and have a sip of coffee, and we'll see how we can start from there. Because I did find some books that I haven't really looked at yet, but by their titles suggest that they may have more information relevant to these kinds of considerations. So today I'll mostly just be reading from some of these books and then extemporizing, as is my usual sort of style. Clocks don't always keep the same time. I set this one digital wristwatch that I got at the Football Pro Shop some years ago, and it chimes on the hour, and now it chimes at 10 past. I don't have a sundial set out to try and figure out if that's related. It's a cloudy day, yet there's enough to keep the earth spinning. I won't mention GW, the CC, so directly as whether with regards to an experiment of sorts to see whether when I publish this video, it will show up with an informatory placard explaining the entire involved, complicated situation in a quick platitude of the authoritative sort. Let's see. Now, if I am to so proceed, what I found the other day were these 3 slim volumes that are from mathematics, and they have some interesting things about them. So this first one's called Finite Markov Chains and Algorithmic Applications. So Ole Hagström from the London Mathematical Society in Student Text 52 has from this library of this man who have quite a few volumes from the library of this guy, and from Cambridge University Press. Now, as I've studied my collections of books, and when I come across them in terms of this as a market for these things, it's kind of curious when you come from some of this ex libris, this same type of person, because you have a pretty good idea that they're pretty good, because they have a pretty good appreciation of books, I can tell. Basics of probability theory, Markov chains, computer simulation of Markov chains, irreducible and aperiodic Markov chains, stationary distributions, reversible Markov chains, Markov chain Monte Carlo, fast convergence of MC-MC algorithms, approximate counting, the Prop-Wilson algorithm, sandwiching, Prop-Wilson with read once randomness, simulated annealing, and further reading. So what this intends to convey are a couple different things. One is that the Markov chain is kind of like before there were neural nets and before there were hidden Markov models and before there were long before there were these large vector machines or what, which are basically just combinations of these with this arithmetization of some coding to arrive at forgiven concepts and category that when they're all clubbed together looking for data and relations is the idea that these vector models just compute these vectors and then kind of just land off in the field of that so that the search can be localized to this partition in a sense. And so then as with regards to the idea of how to look through that kind of thing, it's entirely motivated and is involved by essentially a system involving types and such notions of belief, desires, and motivations that make for a model of cognition. And so then these notions of the hidden Markov models as for the neural nets are just the ideas of that you can take a bunch of numbers and make it so that by training them on the classification of data and providing which ones are right and which ones are wrong, that this idea of the training the data is the one of these cat tossing combinations thing as was discussed in the GAF in a previous talk. The idea that it's basically a sort of genetic algorithm. So what you do is you take and make like 10 million copies of this sort of setup according to its initial weights of its states, that it's a graph and it's got weights, and the weight basically indicates the probability that it will take branch A or branch B. And so you artificially perturb those to small and various amounts to make it so that this genetic algorithm kind of feeds which ones were lean this way or the other way. And you make 1,000 copies, and then the ones who meet the goal that was so required, the survival criterion, are kept, and then the ones that don't are discarded. And so it seems rather this whole idea of like basically playing God with these things. And in a sense it is, but it's not necessarily so much of the way of the, what would you call it, the intelligent design. It's more like you might get what you want, and so one must always take care about what they wish for, and then also that you might get what you think you want, but it might or might not be. So the Markov chains is basically these weights. And so the weights affect to whether, in the course of the Markov chain, which is just a sequence, what goes up and what goes down, or left and right. And then the idea that this Monte Carlo is exactly as what you might expect, that Monte Carlo is a gambling house. And so the idea is to apply different variations of the stochastic, or as a source of randomness, and then from those to see which ones approach the fitness function and which ones don't, and then see if it was regards to those ending up being closer, that by this tremendous case of an expenditure of an embarrassment of riches of computing results, that it so arrives at these kinds of things can make for constant rate flow machines then as a template that, given the data they have and the classifications that they had and more than less what would make for these discriminators or these features in the data upon which it depends on whichever are the analytical tools made to arrive at that those can be discovered, discovering the features, classifying them as the inputs, and then from discovering sample data, the corpus of example, sample, and reference data, and then outliers and exclusions, or the comparison and the making of the contrasted things, to compare and contrast things, how they're the same and how they're different, that then it arrives at that it's a pretty simple thing to express, to relay, that the notions of the neural nets are at once the application of a high technology solution, and at the same time as if it was just kind of the pick of the draw, which ones happen to have some close approximation to expert. So the artificial intelligence and the history and the theory of it, it's not all about these hidden Markov models. They really came to the advent and forefront of this boom in them because of the massive embarrassment of riches and computing resources available to anybody, courtesy Moore's law of the CPU and of the RAM and of the disk and then of the network. So if it wouldn't have been for that, then it would not be economical to expect that you could just kind of take, 10,000 clock cats each with an abacus and give them random rules and one part or the other to adjust the abacus, and then that they so correspondingly output a bit. So these other two sorts of legs of this three-legged stool, there's something to be said for a three-legged dog is always a fine animal, but a three-legged stool is that one of them is neural nets these days, because for supervised and unsupervised classifiers. There are many different topologies of these things, but they basically involve that they're mathematically graphs, and then they have like the hidden layers and anything to do with the way these things can make up for conditions and the rules and the weights and the interchange, the flow of the inputs into these graphs, the flow of the outputs out. That's their thing. So the second leg of this inference is statistical inference. So statistical inference is based on the ideas of probability theory and statistics. This is that there are arbitrarily called a random variable, and a random variable provides values or has values from a support space. And out of the support space is basically a means of sampling, not to say means loosely when it's very involved in the language of statistics, but the method of sampling, say, that results the event of the population being sampled at any particular event, that the draw is called an event. And that where it lives is called a support space, and the population is a subset of that. And then the sample is what we call a random variable. And so then the idea for a random variable is that it may have, according to what the population is, it has a true distribution according to what property of the event is sampled. So an event is always in time series data. It happens at a given time. And then as with respect to any other properties of the event, it's as if regards to basically, say, the color of a ball drawn from a vase, whether it is red or green. So the idea is that if you put 50 and 50 in a vase and you pour one out, then the idea is that it's 50-50, one or the other, by our law of classical probabilities, basically made off what's counting arguments. But if a random variable, we have no idea what's in the vase, only item by item what comes out. And if it's then a truly random variable as of the entire space of the distribution of populations in the entire support space of all the events in the universe, it's basically checking the time, and that's what it is, and that's what it gets. But probability theory is kept a lot simpler than that, in that we just have the idea of one support space, one population, that's it, and then one sample at a time, and one event, that's it. And then with regards to the distribution it has, it's an unknown distribution of a random variable. And then for these different kinds of mathematical distributions that have their shape perfectly well known, by the given defining characteristic of a mathematical probability distribution called the cumulative distribution function, the probability density function. I get those backwards sometimes. Probability mass function, cumulative distribution function, cumulative density function. And the moment generating function, not to leave that out, is that they basically reflect that a given event has a probability of occurring between 0 and 1 only. It's only between 0 and 1. So if it's guaranteed, then it's approximately 1 at least, or maybe absolutely equal to 1. If it's impossible, it has probability 0. And between those is that for a given event, the probability that an item will have this property is the probability. So that's basically the theory of probability theory. And the cumulative function basically says, okay, given from the lowest possible value, negative infinity to infinity, it rises from 0 to 1. And so that's basically indicates that for a given value, when they're ordered, that it will have this probability that you can say that the probability of it being in this way or that way is like to so, and the probability that it would be less than that is like so. So it contains what would be the probability that it has a particular partition in the range. Then the probability function itself is for each value, it's kind of got a property that indicates it's like this is the probability that it will be of a particularly small range close to that value. Okay, these are for continuous distributions. For discrete distributions, it's just values and their count. So then those just add up to then more of like a box plot than whatever is a distribution like the normal bell curve, which is shaped like a bell and named after Gauss. It comes up after these foundations of statistics. So that is then getting into then for these distributions, you can compute what are the estimators, and so that then you can have what would be from the maximum likelihoods of estimators that you can take means, because distributions basically there's a bunch of different kinds of distributions sort of defined by these formulas, so then you can compute from them the estimators. And then the idea seems to be that for these estimators, their formulas, that then it's possible to have for the shape and scale parameters of these different distributions. There's 30 or 40 well-known distributions, and their analytical character is very well explored, like the normal curve, like the beta and the Weibull and the Poisson and these and various and the discrete distributions and the continuous distributions about Erlang, and there's the hypergeometric and with many parameters in shape and scale, and there's a lot of these different probability distributions then that match up these things. So given a random variable, given enough samples, you can start to estimate whether it has a sensible value as a distribution, and also whether it has like a sensible value of hypotheses, because then you can form hypotheses, for example, about the central limit theorem. You can base everything in terms of standardizing and normalizing that. You take the property and basically say, well, the property is between 0 and 1, and the range is between 0 and 1. We've standardized and normalized this, put it windowed and boxed it in a frame, and then thusly this limit theorem in the Gaussian called the cumulative or central limit theorem. The central limit theorem arrives then at that a lot of the properties of the Gaussian distribution are very well known, and so then students test Fisher's test, t-test, getting into chi-squared, make for then that you can take up these estimates at that, and then there are all sorts of tabulated charts and means to work with those is all kind of a thing. So for distributions with a mean, that meaning a centralizing tendency, this central limit theorem makes a lot of things really tractable. It's a central feature also in the practice and the application of statistics. It's basically the contents of the first 5 or 6 courses of statistics usually. Methods and means, that's about it. But not all distributions have centrality as their thing. Some, for example, are bloated on the front and back, or some are just absolutely flat. So besides a uniformization limit theorem, which kind of decimates everything and brings it down, or this kind of anti-central limit theorem, which is that things are polarized, those are kinds of ways to help look at and understand the school and the field of this thing. That just like when you have the neural nets and something was like, well, I see you've made a supervised classifier and it always finds Waldo, but what you don't know is it's looking at it upside down, and if you put another Waldo on it, it will pick the dot or something like that. That it's just got a weakness in the analysis. It's got an error mode. That's similarly when things are built to follow one thing, then it's not necessarily so. And then in statistics, we have this thing that's called the error record. And then the error record, it gets into reasons that when there's things like the long tail or why that otherwise these usual sorts of generalizations don't hold, then is for these various applications of kind of an overall technique of at least like, well, we're going to have triple central uniform anti-central analysis and help figure out all these things that is kind of its own field by itself. Because then otherwise, just like the neural nets, you can say, well, we'll just take 50 different neural nets and see which one comes back and they kind of agree or come back together, or just one, whatever works, you know. Then in these statistical models, then when you're looking to first find a distribution that's relevant, and then find its shape and scale parameters that are relevant, and then use that for the data that you have to estimate whether it's valid that the data that you get will match those or not. So you can establish, according to the statistical method, which is like the scientific method, a hypothesis which will or won't be invalidated by the gathering of collection of samples if your experiment is designed well, if it's designed reasonably and doesn't interfere with the sampling itself. This statistical inference is this great second leg of mechanized inference, artificial inference, say. So this third kind is the expert system. And so the expert system is the idea to codify knowledge in a symbolic form and its connections, representations as of a grammar, linguistically, and to make it so arrive that according to rules and for example, derivations or mathematics or the capriciousness of whatever the rules may be, to make an expert system. So in these finite Markov chains and algorithmic applications, a lot of that is with regards to the first. It sets itself up with like a sum over terms, and so it's got sequences are an infinite list of terms. There's a first one and an ith one. An I ranges from 1 to infinity. And it's similar when they have a series is the partial sums of these that added up. So it's the sum of a sequence from I equals 1 to infinity. And so these Markov chains are those basically, and then they just have it that each of the terms as they're modified along have transition diagrams according to weights or the probabilities. And then the idea is to figure out the ergodic, what happens to these over time. And so the recurrence relations are another key thing to figure out, the umbral calculus, the calculus of finite differences. And then as with regards to these functions, and then the qualitative aspects of the resulting functions, properties like irreducibility and aperiodicity. And then with regards to information theory, like Wolfowitz and stuff like that, the information theory with regards to signals, that it results that all kinds of Markov chains are just signals over time, and the entire field of signal theory basically considers them all kind of the same. That then the idea is to figure out that in these ones, that some of these techniques make it so possible to arrive at things that then will pull together these things and make it so that there are forms, and then that they can be made up so to, for example, to prove that a Markov chain, Monte Carlo chain, converges sufficiently quickly to its equilibrium distribution. When that's being able to say an acceptor or rejector network, which is the idea that given a formal language of inputs that you can determine by rules whether it's accepted or rejected, has that these are the building blocks of all these things that are all these things, which are for mechanized inference that can operate on tokens and not know what they're dealing with. So why that's relevant to the swath is that when it comes to this dimensional alternator and dimensional resonator, then the idea is to associate it with such notions of a random motion or the Brownian motion or the non-Brownian motion that is possible to consider for these terms of the oscillation and restitution and dissipation and attenuation, that these Markov chains will have these weights so corresponding with those. So then it would be possible to determine for these given kinds of things what would be the tendencies to stay a course or drift from a course, for example, the tendency to go left or right, vis-a-vis these other kinds of things. With regards to computing, where the idea of the swath integral is this, to compute the form that makes for a straight line in terms of all the dimensions, one dimension. And so it's possible to arrive at like, well, I want to stop on that dime. The idea is to say, well, your inputs are not like infinite amount of time in a measuring stick. The inputs are the last 10 inputs you got and the last time you saw the dime and your estimate when it's going to arrive at that dime. So then the idea is to compute that as readily as possible. And so that's not really what we're looking for. And I thought this next book might be more what we're looking for, and it's called Collocation Methods for Parabolic Equations in a Single Space Variable. And this looked most promising. So I'm going to look at that in a minute. This is just something about general relativity. Cosmology in 2+1 dimensions, cyclic models and deformations of M21 by Victor Goeman from the Annals of Mathematics Studies at Princeton University Press. And what it's about, it was written in 1989. It's got Zollfrei deformations of M21, the general theory of Zollfrei, Zollfrei deformations, a relativistic approach to Zoll phenomena, Zollfrei deformations of M21, the generalized X-ray transform, and the Floquet theory. Now, I've heard of Floquet, 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 or Floquet, it might be Floquet, but I imagine it's Floquet. A relativistic approach to Zoll phenomenon, though, that might be rather interesting. In this paper, a cyclic model will mean a compact Lorentz manifold with the property that all its null geodesics are periodic. So Lorentz these days is really related with general relativity for any kind of solution to the gravitational field equations has to make it so that it's invariant in the Lorentz. And so what you have is for special relativity, it's kind of in the inside of that, and general relativity, it's also kind of inside on that, but it's also like to either side of that. And so then they have what's called Lorentz factors, and then so the Lorentz factors makes for it's like, well, if you got any kind of space inversion about that, it would have to be according to these factors, and so you want to keep it all inside there because it's the Laplacian and the second order and square, and so it keeps the triangle rule on down all inside for everything, so that something that's linear stays as linear most absolutely, and then anything outside is its own thing, and then that all its null geodesics are periodic has that is basically saying that a geodesic is any of these lines in this space and time and things that will naturally kind of flow along in this Lorentz manifold. So Lorentz manifold has this properties that anything in it is so governed this way. And so the idea that the null geodesics are periodic basically makes it so that they is assigned them a degree of freedom. And so the spatial of Einstein's is similar in a sense when he says the spatial here has made it for special relativity, the spatial, that they do not have a null geodesic. In fact, the geodesic is kind of determined. But the geodesic is actually kind of determined by this general relativistic term. And so what that means is that this basically makes for the same thing as context from the discussion of Einstein of the bridge, the centrally symmetric, and the white holes. That this is the idea of like a black hole, everything falls in, white hole, everything comes out. And so then this null geodesics being periodic is kind of the same thing. It's assigning what's a singularity, and it's kind of a trivial vacuous and null singularity because it's the principal branch everywhere. It's the classical position of these things to be in a multiplicity theory. So, such a model is cyclic in the sense that every space-time event gets replicated infinitely often. So in this kind of cyclic model, it's basically assigning this functional freedom to everything, a single point in space-time. So Einstein is against this, well, that's the one I was reading in, because he's like, everything should be connected in one system. But what this does mathematically, it says, abstractly, it says, hey, we got to deal where it's all bound down by this mathematics. Something's got to give. So I'm going to start with a very general sort of model where everything gives. Such a model gets replicated infinitely often, has an infinite number of antecedents with identical pasts and futures. We should warn the non-expert that this is not what relativistics usually mean by cyclicity. This term is almost always used to describe periodic solutions of Einstein's equations. In 2 + 1 dimensions, this implies that the metric involved is conformally flat, and as we shall see in section 11, this is practically incompatible with cyclicity in our sense. So that helps to reflect that Einstein really always kept things linear and on that being on the level for that. Then it was indisputable, and anything else is like, well, you have to qualify every other thing you say. And so he's like, I'm not saying nothing. It's just all linear and on the level. So here, and then while that is so, that he has some great, sort of claims that for something like, well, this is coordinate free in the sense that over here it's in this frame and it's in this coordinate space, and over here it's in this frame and it's in this other coordinate space, which affects to reflect the geodesic being conformally flat, so that everything goes straight. Gravity is always down. But how the patchwork is between this metric and that metric, it's up to you. So that's just goes to say that then these other solutions and systems are of many various authors. We will call a Lorentz metric, all of whose null geodesics are periodic, a Zollfrei metric. For the etymology of this term, see section 1. Now, etymology, of course, is always key because it is the word. Notice that the property of being a Zollfrei is conformally invariant. So conformal mapping basically means like affine projections and affine transforms. It's like it preserves metrics, angles, preserves a picture of the shape. You can transform it back. And so conformally invariant usually means that it's as if there's no discontinuities. So even though, and I need to check to make sure that's what he means by the word here, because otherwise you'd think that these, adding up these different things to the Lorentz invariance would make it not Lorentz invariant. But he's just saying it's conformally invariant. This is because two Lorentz metrics have the same null geodesics if they differ by a conformality factor. The metrics of these two different spaces with different bodies as them that are different frames. Another way of stating this fact is that the trajectories of light rays are independent of the metric structure of space-time but only depend on its causal structure, i.e. the specification of the future of every space-time event. So this is this Einstein's geodesics of those the spatial of the special relativity, which goes off in a fleetingly fast thing, and usually in terms of our classical milieu, as everything is much less than the speed of light, in terms of the frame we are in, that it really is matter of factly that's usually the most unbounded thing. But in the highly relativistic environments, he's saying that that's not so necessarily going to apply, and that light speed is just free in this manner. The Zollfrei problem is interesting even in dimension 2. In fact, as a warm-up for the problem in dimension 3, we'll briefly describe what happens in dimension 2. So, and then it gets into configuration space and the orbits. So this is pretty modern. It's got orbits. He's talking about the null-free, Zoll-free. But what I'm curious is just to see what, because then it gets into just the usual sort of development. And then he starts talking about the anti-de Sitter universe. And so this is the mathematical models where it's like, well, everything is open, so we just kind of project it, and then it's trying to solve gauge theory out in this, and it's like, well, that's a little far out. We got to solve this stuff a little bit closer, and it does not necessarily say that's conformal invariance. Make some use of the ideas of Paneitz, Paneitz, and Segal, Segal. And I was hoping to just see what was the etymology bit. It would be nice. This is the foreword. Before we get down to business, we would like to express our appreciation to the many persons who have helped us with the preparation of this manuscript. The material on the infinitesimal deformations of compactified Minkowski space could not have been written without the help of David Vaughan. So, Gaiman. similarly, our original version of this material using spherical harmonics was 3 times as long as the Harish-Chandra module approach described. Sections on the micro-local properties of the X-ray transform. That'll be interesting because that gets in this near-field, far-field bit and gets into the fact that light is optical and nuclear radiation, that protons have a long lifetime and these kinds of things. And those vis-a-vis matter and charge, making a four-legged sort of stool of this kind of thing. Last but not least, the stimulus for writing this paper was Irving Segal's monograph, which convinced us that the Einstein static universe still has to be taken seriously as a cosmological model. A Riemannian metric on a complex manifold is called a Zoll metric if all of its geodesics are simply periodic of period 2 pi. So, and there's about 2 folds. Funk wrote a seminal paper on Zoll 2 folds in which he posed the following problem. Find all Zoll metrics on S squared which are C squared close to the standard 1. All right, so these are they would have to pick like a center and kind of branch from that, and then it's just kind of a means that how else you might approach that is that that's usually just considered the mechanics of the body itself and the space contraction and stuff. So here that's a little bit more framed in terms of how to arrive at space contraction. But one might imagine these Zollfrei metrics would have some models of them. So this next item is where I want to hope to find something about these collocation methods for parabolic equations in a single space variable. Because it kind of affects to reflect that it's like I want to figure out how that stops on a dime, and so it's spelled collocation, kind of like the collinear has 2 L's, C-O-L-L-I-N-E-A-R. This is collocation, C-O-L-L-O-C-A-T-I-O-N, collocation. And then the idea is that it solves it for a single variable by this parabolic form, or the quadratic, that the parabola is kind of the same as x squared, or the quadratic, the root. So the parabola and the quadratic are just kind of like the inverses and reciprocals of each other. Let's take a look at this book. Lectures, Notes in Mathematics, number 385. Jim Douglas Jr. and Todd DuPont, University of Chicago, 1973. Previously unpublished research in collocation methods done over the past 2 years. Problems involving more than one space variable are not considered here. And so the chapters are titled Global Error Estimates, Superconvergence Estimates at the Knots, the K and OT, the knots, Local Superconvergence by Local Refinement, a smooth collocation method and applications to eigensystem approximation. So this is a book about numerical methods, and I was hoping it was a book about analytical methods. And then for these, so for cubature after the quadrature, which are the great many varieties of analytical numerical methods that are quadrature or cubature, and so affect to reflect that they can compute given a bunch of different things, very much of them, given not so much of them, that arrive pretty close in limited means, make it so that then an embarrassment, which is kind of a new unit of computing resources, can compute it in a reasonably brief time, called I mentioned, what is it, a coffee break or something like that? A smooth collocation method and applications to eigensystem approximation. And so the authors recently had introduced a collocation method for the numerical solution of the parabolic equations, c of x to u, d of times du of dt in the partial minus a of x to u, or d squared u or dx squared, minus b of x to u, d u dx equals 0 for x between 0 and 1, t between 0 and big T. And then with this, that u of x comma 0 equals f of x, and for x between 0 and 1, and u of 0 t equals g naught of t, and u of 1 of t equals g1 of t of 0 t of t. So this is set up kind of how the swath is being talked about being set up, as for between 0 and 1, and 0 and 1, and 1 and 0. And then trying to figure out for this, it says, based on the use of an Hermite piecewise cubic space for approximation in the space variable, showing the optimal order convergence for the approximate solution of that of 1.1 results for a sufficiently smooth U for the set of collocation points chosen. This manuscript, which shall generalize extend these results in many ways. Says, so he's talking about the Hermite piecewise cubic space. And so that is something I'd be considering, because you got the Pythagorean and about the a squared, b squared, c squared, d squared, dot, 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 and that in the higher dimensional space. And you got the triangle law, triangle inequality, Cauchy-Schwarz, and that's used for everything. And that's basically what is the metric. And then in the far field is like, that's also the norm. And then for what is distance and all that. So the idea is to make very careful the survey of the terms that exist, like metric and norm. And then with regards to the derivations that provide what they intend to convey, and then for things like momentum and inertia, to keep difference when they're difference, and then when it's inertial momentum and momental inertia, either way, to help identify to reflect whether changes in the dynamics that come into play in terms of the definitions, so that you can compare and contrast them and they stay rational and relevant. So I'm not really drawn too much right away from this, but I'd kind of hope to, and I should read this a little bit more. But what it would provide me is a lot of what goes on into this interpolation and extrapolation, because what it intends to convey and what it pretends that it provides is that for some of the situations then where these collocation techniques, which are basically given values, what is the input, which arrive at a different value. So that's why it's so deemed relevant, and this could help finding these values, is expresses that in some cases what would be nonlinear terms do have linear solutions. So what this parabolic equations, some collocation methods of the parabolic equations, suggest that this optimal order estimates, then an extrapolation is applied in the evaluation of coefficients in the differential equation, so that the algebraic problem at each time step becomes linear, even for the nonlinear equation. So this is when we get involved in this rank lowering, or these symmetries, submersions, and sheaves, that this is kind of finding a submersion, and it's relevant because it's probably this fractional analysis, I imagine. It's this extrapolation. Kind of when we were talking about the extraordinary differential equation, that it was for non-integer values, and it's supposed to hold good between integer values. So that's what I imagine the authors are talking about here. A special case where collocation is used in both space and time. An approximate solution is sought in a subspace constructed as a tensor product in a seen piecewise polynomial space in time. The analysis of the error in these methods, both straightforward and extrapolated, is a forerunner of the basic analytical tool of Chapter 2, and is shown the optimal order accuracy in space and time occurs. So this is pretty cool. I would be considering what are the requirements of like what gets computed when, vis-a-vis how is this solved, and things like when you have two things, or the three-body system, and these kinds of things. So we got a mention of Rodrigues' formula right up front, and it says in this form, it's b double prime sub r of x is 1 over 2, this quantity 2r minus 2 factorial, times the r minus 1th derivative of x to the r minus 1 times x minus 1 to the r minus 1. So this is a great thing going on with this x squared minus x, and then their powers and these terms and this factorial, and then the increment techniques which make sure for addition formula, and indexicality. Indexicality is a great thing to be able to arrive at, that given the order of something or its offset, its index, that then it can be arrived at its value, vis-a-vis having to compute everything and count it all the way up or multiply it all the way down. That this is a great feature that's provided by Rodrigues' formula. Elementary calculus indicates the roots of that equals 0 are the double roots at x equals 0 and x equals 1, and exactly r minus 3 simple roots at points eta sub j, such that the eta sub j's are ordered between 0 and 1. And he says, here's the interpolation operator, says from c to the p here, c to the 1 of the identity to the p to the r of the identity, that it's like tv times x equals vx, and t sub r v prime x equals v prime x, and then t sub r v eta j equals v eta j. So that's not necessarily going to be so describing, except it is, he says, when those numbers plug back in and solve that form, then interpolate it among those numbers as according to what their solutions of this form. And so if you find the coefficients of r, you find r here, and that will give you an order, that will be sufficiently high order that you compute this very high order polynomial equation, and it crunches down to interpolate among these three values that are like a, b, and c between 0 and 1. So usually you use a rank lowering type of operations to hopefully get at something to be solved on a lower order. And here it's like, let's take something real cheap and take it up to a real high order, and they'll arrive at that in the middle, it breaks down to what's somewhere falling in these parts. So, and that's a great idea. I mean, that's just making use of an expansion of things, and then being able to say that, hey, once it gets up above these particular high powers, then you can say that it will fall back down among these different ranges and partitions. He says that then let this r plus 1 factorial over r plus q factorial, x minus 1/2 to the quantity q minus 1, b sub r of x, or before we were talking about b double prime of r, equals this thing by Rodrigues' formula. He says it is a simple consequence of the Peano-Kernel theorem that the interpolation error has a representation. And then he provides an error term. So then he talks about that all functions, the Sobolev space of functions having L squared I derivatives of order r plus p plus 1 on I, where the kernel is given by this Peano-Kernel, and then this form. And then he says the error expression can be differentiated. So modeling the bounds of the error term helps a lot, because then you can guarantee that somebody that says, hey, this will never be exact, or you might look out. You can never say it's exact or not exact, but the error terms will be limited to these bounds, is the idea. These orthogonalities play an important role in analyzing our collocation methods. So what I'm curious is if it just briefly mentions what this extrapolation is, or if that's what it is. Let us introduce another interpolation, where interpolation and extrapolation sometimes are conflated to be the same thing. Interpolation is like between 2 points, and extrapolation is like as of among points. So this extrapolation might be what it is when they're talking about this interpolation. We shall assume that A and C are bounded above and below. Continuous time collocation method. So this would be pretty useful, because it would arrive at these analytical forms in the middle that kind of are what can then be broken down. But I'm looking for something that's going to end up being of simpler parts, and that then carries around itself in its own terms, kind of a thing. That what is computes where it's going, where it is, as it goes along. Uniqueness for solutions. And he talks about the authors write a bunch of different derivations as they build these terms and their usual means of arithmetic, as about usual things to do with the metrics and norms. is about these forms, these two forms, I imagine you'd say, about the additions, and then about the transform settings of some of these things. And what results coefficients, discretization in time by finite differences. Hence, that the extrapolated version is 5.12 are special cases of the full collocation procedures to be studied in the next section. So you might have some more of the development of the analytical with regards to 5.12. Note that 5.12 represents the linear system for the coefficients. Equation 5.1 is algebraically nonlinear if the differential equation is. It is possible to extrapolate the values of u and the coefficients in order to avoid nonlinearity in the algebraic problem. Let u tilde n equals 3/2 un minus 1/2 un minus 1 and consider the extrapolated Crank-Nicolson collocation method that says c of u tilde n dt u n minus u double x to the n plus 1/2 minus, so it is in a sorts of like to fractional powers, where it's in the double integral, double derivative, minus b of u tilde n comma u tilde n sub x epsilon ij equals 0 for I equals 1 to m, j equals 1 to r minus 1, and n equals 1 to n minus 1. Subject to the boundary conditions and the initial conditions. It's also necessary to obtain the vector by some startup procedure before using the equation to advance the approximate solution in time. The analysis, the convergence of the solution, is a perturbation of the argument given for the unmodified Crank-Nicolson procedure. So I guess that's a matter for following from after Rodrigues formula to learn about this Crank-Nicolson procedure, Nicolson, Crank spelled C-R-A-N-K. See if that is a pretty well-known thing. Well, I'll look some more for that at a later date, some of these things. So some quick quotes here. This is this Davies book I read, and so it's from the 80s, and I kind of wish I'd read this then, but then I might have been biased in terms of what I kind of thought of what I thought that particle physics and field theory was. It says, the astonishing result of the Wheeler-Feynman analysis comes about because, in their theory, the electromagnetic activity of any individual charged particle cannot be separated from that of the entire universe. And so this is that, or for the Wheeler-Feynman and the advanced retarded, and this great debate in the foundations of the electron physics, and ever since Maxwell and that they came up with this discussion of these things, that it's one of these great things in this, like, can there be backward, what is, because the advanced would be backwards, and so trying to figure that out. He said the waves produced in one place cannot be entangled from the echoes they induce even from the most distant regions of the cosmos. Moreover, because of the ability of advanced signals to propagate backwards in time, there's no 1,000 million year delay for the echo to return. This was the problem about a gravitational echo need to produce a force of inertia. Therefore, every humble radio transmission becomes literally a cosmic event. So it helps to effect to relay that, and there's like a standing wave, and radio waves aren't, like tiny little dots. They're like yanking on the entire chain. The whole in its parts. The Wheeler-Feynman theory is Mach-ian in the sense that it seeks to link the local and the global in a network of influences, and suggests that we may understand individual physical systems only by proper reference to the whole. And so that I wanted to read that section just because then it gets into David Bohm and wholeness in the Iplicate order, which we've considered here, and there's a copy here, and trying to figure out, and then he talks about the hologram and talks about Mach-ian things. And then he has a great little discussion of like other writers such as Fritjof Capra in the Tao of Physics and Gary Zukav and the Dancing Woolly Masters have emphasized the close parallels between quantum physics and Oriental mysticism, the holistic worldview. More generally, it is possible to regard a quantum particle as possessing well-defined attributes such as position or motion. Thus, we can find the position of a quantum particle only within the framework of a macroscopic measuring system. The particle's position is really a collective or holistic concept. when I see collective, I think bad things. So that's something else. Anyways, that's a bit of a section I wanted to read from that. And then this other thing was this. It's an anthology of Juan Borges. So Borges was an Argentinian writer, and he's famous for his stories. And he also had a great interest in the infinite. And so sometimes he would make a quote or have something like that. And there was this one section here. I'm not sure what it was. He's talking about Romerstadt and judged as vindication of eternity. He argues that the number of experiences possible to man is not infinite, and that a single repetition suffices to demonstrate that time is a fallacy. Unfortunately, the arguments that demonstrate this fallacy are not any less fallacious. Pelagic was in the habit of running through these arguments with a certain disdainful perplexity. So, a lot like T.E. Holm, Borges, at some points, indicates that what he has is a theory of discontinuity in time. And at the same time, then he's a Platonist because it's kind of a rejection of these usual Platonist notions. And if he's got to reject something to be a modern man in the philosophical sense, like for logical positivism or what, that's kind of what he chooses to get. Like when he talked about Heidegger and after Nietzsche, after Wittgenstein, and like the throwing out logic, throwing out deism, and throwing out time or continuity, then that's something that Borges gets to sometimes. But here he's just talking about that he's talking about someone who's a little bit stronger in that course in criticizing him. The dangers. Toward dawn, he dreamt he had hidden himself in one of the naves of the Clementine Library. A librarian wearing dark glasses asked him, "What are you looking for?" Haladik answered, "God." The librarian told him, "God is in one of the letters on one of the pages of one of the 400,000 volumes of the Clementine. My fathers and the fathers of my fathers have sought after that letter. I've gone blind looking for it." He removed his glasses, and Haladik saw that his eyes were dead. A reader came in to return an atlas. "This atlas is useless," he said, and handed it Haladik to open it at random. As if through a haze, he saw a map of India. With a sudden rush of assurance, he touched one of the tiniest letters, and a big voice said, "The time for your work has been granted." And he woke up from his dream. He remembered that the dreams of men belong to God, and that Maimonides wrote that the words of a dream are divine when they are all separate and clear and are spoken by someone invisible. This is a story of a man who was captured by a murderous cabal and sentenced to death, but he made a wish to experience time as if it went on forever. I guess it beats Friday. Huh? This is the old joke. There will be a quiz. Hey, have a great day. June 29th, 2024, Seattle, Washington. From a desk of Ross Finlayson. Until next time.